Hello everyone, welcome back to this channel. So today we are going to continue our discussion on decision trees. In the first video, we saw that how decision trees work. We saw the basic fundamentals, and we discussed that there are certain metrics which help us decide how the branches of these trees are created. So what will be the decision? What will be the attribute basis which the splitting will happen? So today we are going to continue on that part with the second video in this series and see how a tree is constructed using these four metrics which we discussed in the previous session. So the four metrics are entropy, information gain, Gini impurity, and chi-square test. So one by one, we will take each of these metrics and understand how these metrics work. So to start off, the concept of entropy. So entropy is a way to measure the level of disorder or uncertainty. So as the name suggests, you would have studied in high school physics that entropy is the order of disorder or the disorderliness in any sample. So sample in our case would be a data. So a data would have certain categories of the data can be divided into certain categories having certain the values of any data set, whether it's categorical or continuous, or whether it is a numerical data or is a category yes, no, true, false data. So every item on that data set would have a certain frequency or the number of times it would happen. It would be occurring. In case of continuous data sets, we would have ranges. So each range of that data would have certain number of values in that range. So to understand more, let's see how the mathematics of entropy works. So let us start with the probability. Let Px be a probability. It's a probability function. Then 1 by Px will be the surprised or uncertainty. So to understand this better, let's say a probability of something happening is 0.9. So 1 by 0.9 or 10 by 9 is the disordinance. It is the surprise. So in other terms, let's say we have a coin and coin is 90% likely to give us heads. So if tails come, we will be surprised. So the probability of if heads is 0.9, the surprise on tails, the probability on tails would be zero point 0.1 and 1 by zero point 0.1 will be 10. So the surprise on getting tails would be 10, whereas surprise on getting a head would be 10 by 9, that is 1 by 0 0.9. So 1 by px is the surprise or the uncertainty. To bring this uncertainty measure into a scale, we use the logarithmic scale. So log 1 by px is the term used to capture this surprise or uncertainty within a scale. And in data science, log to the base 2 of 1 by px is used as the measure. So the y can be checked out. You can Google it. We won't be covering in this presentation to make it a time-bound presentation to stress more on the concepts to be covered. So entropy can be generalized under this formula. Now we see log 2. Uh, Let me get a pointer here. So yes, this can be written as log 2, log 1 to the base 2 minus log probability to the base 2, if we could recall the laws of logarithms. And that again can be the log of 1 to the n to any base is 0. So this can be written as this. And the total entropy can be used as a summation of the probability values. So this is where this formula comes from. So now how do we split using entropy? So let's take a sample data set. This is similar to the data set we used for an example in the first presentation. Now let's say that this data set has three attributes and one outcome. So in the previous presentation, we saw that the outcome would be whether a child is allowed to play outdoors or not, depending on the weather conditions, whether it is sunny, humid, rainy. So we had three attributes. One was temperature, one was humidity, and each attribute had a certain set of values. So humidity could be high or medium, the wind conditions could be high, medium, and things like that. So we have generalized that here, and we are using three attributes, out of which two are categorical, taking true and false, T and F values, and attribute 3 could take continuous values. We have taken continuous values deliberately just to understand that in real life that we could get a mixed data set. But for this presentation, we would be focusing on the categorical data set for the sake of example, because the continuous and the mixed part is covered in the upcoming presentations. which you will see in this series. So entropy, we saw that formula in the previous slide, and now entropy of S, that is the outcome or the target variable, is found out by calculating the total frequencies of each data. So we count the yeses, which are 4 here, and we count the nos, which are 5 here. And the total number of data points is 9. So for the yeses, the entropy is 4 minus 4 by 9, log 4 by 9 to the base 2. And similarly, this term is for the no's. So now we have the total data set entropy, the total outcome, the target variable entropy. So in other words, we can say the disorderliness in the outcome. And as an intuition, we can see that this, because we have out of 9, we have a split of 4 and 5, the disorderliness is higher. So if we had 1 or 8 or 0 or 9, this term would have been much lower. The disorderliness of this data would be much lower. So now taking entropy for attribute 1. This is the attribute 1, and we have taken it separately and taking it forward. Now this attribute 1 has certain trues and certain false. So if we count the green arrows, there are 4 green arrows, so there are 4 true values and there are 5 false values. Now each these 4 true values is either leading us to an outcome of yes or no. And we see that for the green arrows, there are 3 yeses and 1 no. So for true, there are three times out of four we have yeses, and one out of four we have no's. The total entropy of true is calculated in this fashion by putting the formula for entropy into use. And similarly, the entropy for the false is calculated because the false, the red arrows we see here, there are there is one yes, this one, and the rest of them are no. So one out of five is a yes and then a no. So this is how we get the entropy of. Now we have three entropies. One is for the outcome, one is for and two entropies, two conditional entropies for the attribute one. So I saw that I say conditional because there is a condition that for the true data points, what is the entropy, and the false is what is the entropy. And now in the upcoming slide, we will see how these entropies are put into use. But before that, let me introduce you to the concept of information gain, because these two are related to each other. Information gain uses entropy as a variable for calculation of for information gain. So information gain is the difference in the uncertainty before and after the split. So what new information are we acquiring about the entropy or about the uncertainty or disorderliness of the data? This is what information gain measures or gathers. So the before the split, we can say, as an example, we say that there is a high uncertainty in the data, and after the split, our goal is to have a lower uncertainty. So we need to have a lower entropy after the split. And the formula for information gain is the initial uncertainty minus the uncertainty after the split. So this is the gain of information, or the gain in terms of difference of homogeneity, or in terms of the orderliness or disorderliness of data. This is what information gain is giving. And mathematically, it is denoted with this formula, wherein this formula can be explained as information gain in total is calculated by the entropy of the data set before the split, that is the outcome variable. So before the split, we are using outcome as the starting point. The entropy of this is calculated, and then the entropy, the conditional entropy is of the dataset after the split based on attribute 1 is calculated. So this is what we are doing. And in the previous slide, we saw we had these three entropies wherein this was, so let's see. So the formula for gain, in other words, can be written as the entropy of the dataset minus the summation of conditional entropies. And we are giving weights to these entropies in proportion. So we'll see how this works out. So this works out in the following manner. The total outcome or the entropy of the dataset before the split is this, and then the weights of 4 by 9 and 5 by 9 are given to the true and false entropies, because the true values, there are 4 true values and 5 false values in attribute 1. So the weights are given accordingly to trues and false. And we already have the entropy of ST and SF. which were zero point 0.9 we calculated in the previous slide. We are putting these values here and we get the total information gain of 0.2295. So this is the gain of information or the change in the orderliness of the data or the change in entropy of the data before and after splitting. Now, this information gain that we have calculated for attribute 1 is also calculated for other attributes, which in other case, with us, we have attribute 2, which was found out to be 0.0072, which is much less than attribute 1. And hence, we will proceed with attribute 1 basis information gain. So now, let's move on to, we have covered entropy and information gain. Let's move on to Gini impurity. So what is a Gini impurity? Gini impurity is a way to measure how mixed up a group of items is. So if in a bag we have 10 items and we have 5 of each, the 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 bag carrying these 10 items is very well mixed up. So it will have a high level of impurity. So in other words, we see that lower Gini impurity means the group is pure. So if we had 9, so let's take a bag with black and red balls. If we have 9 red balls and 1 black ball, it is less mixed. It will have less Gini impurity. And if we have 5 of each, then we have high Gini impurity, which means the group is more impure and more mixed. How is Gini impurity calculated? So this is a simple formula wherein 1 minus summation of the probability sum or the proportion of items in class I within the group. So let's taking that example forward, where we have a probability mix of zero point 0.9 and zero point 0.1. So if we had 9 red balls and 1 black ball, the probability of picking the red ball is zero point 0.9 and black is zero point 0.1. So the Gini impurity in this case would be calculated putting the values of these two probabilities in this formula, taking the summation, we'll get 0.18. And similarly, if we had a mix of zero point 0.5 and zero point 0.5, this Gini impurity would be 0.5. So lesser the Gini impurity, more is the homogeneity of the mixture. Purer is the mixture. So Gini impurity, in case of the data set, it is we again take the weighted average. We take the proportion of items for each item. We take its proportion, and how it is implemented we will see in the next slide. And using this Gini impurity, we calculate a metric called Gini index. And Gini index is the weighted average of Gini impurities after a split. So now let's see how Gini impurity is calculated. So this is the formula. Now here we see that there are 4 true values leading us to 4 values in outcome. So we see that there are 3 yeses and 1 no in our case. So 3 yeses, 3 by 4th proportion of this, and 1. This is same as we saw in entropy also. We did that. We took the proportion 4 by 9 and 5 by 9. In this case, now we have for true, for this partial part, for the true data points, we have the distribution of 3 and 1, 3/4 and 1/4, and this is the Gini impurity for the trues. Similarly, Gini impurity for false is also calculated. We have 5 false arrows, out of which 1 is pointing towards a yes and 3 are pointing towards a 4 are pointing towards a no. So out of 5, 4 are no and 1 is yes, and we calculate the Gini impurity for falses, which is 0.32. Now Gini index is calculated using these two values that we have just calculated by giving them weights. So that's what we were talking about. So a weight of 4 by 9 and 5 by 9 is given to trues and false, because here we have, out of 9 values, we have 4 trues and 5 falses. So 4 trues into Gini of trues, then 5 falses into Gini of falses, and we get Gini index. So putting the values here, we get a Gini index of 0.344. So now we have found out for attribute 1, the Gini index is 0.3444. Now similarly, for attribute 2, we found that it was calculated as 0.4889. We have not taken the calculation. So now, how does it help? Combining these two results, what we have seen is we have seen information gain, we have seen Gini index. So in both the criterion, we see that this is the choice to go, because attribute 1 has higher gain and lower Gini value. So this is the sample is likely to be purer, And if it is giving purer samples, which means it is taking us to leaf nodes, it is taking us towards decisions where we have pure leaf nodes. So this is what is happening. Outcome of yes, no, we have to make a decision. What is the attribute to start with? We see that there are four trues and five falses for attribute one, but and again, five trues and four falses in attribute two. Since the distribution is same, they are likely to give us same outcome. This is the first feeling that we get, right? But what is happening is attribute is one is somehow giving us a better result. How is this happening? How is this happening? We see that intuitively here. So this is a very basic intuition that we can get, that the truths, there are four truths in attribute one. And what is happening? We have four outcomes of yeses in the target variable. So these truths, one, two, three, and four truths are giving us, leading us to the right decision. And similarly, there are five falses, which are also leading us towards a no. So there is some parity between the target variable and the attribute one. We see that there is some link, and attribute one is better capturing that link through the matrix that we have just used in the previous slides. So this is the intuition behind that split. Why attribute one gave us better results, and why we chose attribute one to as a starting point for the splits. So now we know attribute one will give us better results. And similarly, then we move on and find out the next criterion. It could be any of the remaining attributes to find the next split. We had compared attribute one with two. We found that one was giving us better results. Now, after we have done the split, we check again how different attributes are measuring up against each other. And then we finalize what split to be used. So now moving on to the chi-square technique. This is the fourth technique in our presentation. What is a chi-square method? Chi-square method gives us statistical significance of difference between child nodes and parent nodes. See, in essence, what we are doing is every method is giving us a difference between child and parent node in some or the other way. So this is a statistical measure we are using between expected and observed values. This is one way of doing it. Previously, we have done it with probabilities. We have used various other metrics using various other basic variables. How does it work? We will see in detail. These are the steps being captured, and in the upcoming slide, we will see these steps put into action. This is the formula for chi-square: observed minus expected values. The summation of that, this basically observed minus expected squares divided by expected values, and the summation of these values give us a chi-square. And then in the example in the upcoming slide, we will see how this is used. We split the data using a chi-square. So again, let's start with attribute one. Again, we have to compare which attribute is the best, giving us the best split. We start with attribute one as a starting point. So attribute one, we see that there are four yeses and five nos. And let us create a table out of these values. How we create this table is there are three trues and one false for yes. So okay, we can look at it another way. Let's take trues at a time. So for the trues, there are three yeses observed and one no observed. For the trues, there are three yeses observed, one, two, three. Sorry, this is the false. So for true, this one, two, and three. These are the three yeses, and one no is observed for true values, which is this one. And similarly for false, we have 1 and 4, and we find out the total of these observations in here. So what we are doing is we are leading up to the calculation of chi-square. And this is how we are proceeding there. Now we have observed values for all the four parts, the grid where we can divide is, because we have two decisions here, it becomes a 2 by 2 grid, this which is captured here, and we have totals of each. Now moving forward, this is the most important step. We are trying to find out the proportion of each kind of result in each kind of value in the attribute. To simplify, attribute one has true and false. What is the proportion of trues and what is the proportion of false? So we see that there is 1, 2, 3, 4 trues. So 4 by 9 gives us 0.44, and this 0.55 is obtained by dividing number of falses by total falses, by the total values. So there are 5 falses divided by total, which gives us 0.55. So these are the proportion of trues and proportion of false. Now we need to find the expected values. How do we do that? Now we have this ratio, which is the proportion of trues. Now we have the proportion of trues here. Now let's see yeses and nos. So there are total of 4 yeses. Now, if you multiply 4 into the proportion of trues, we get this value, 1.78. And similarly, we have proportion of false here as 0.55. And out of the 4 total yeses, how many are expected to be false? By multiplying the total into the proportion of falses. So basically, this has been split into a proportion of this and this. And similarly, we do the same for no. This is very important step. Let me again repeat. So what we are doing is we are calculating the proportions of trues and false in the data, which is 4 by 9 and 5 by 9. And then we see for the total, there are 4 total of yeses. Now the 4 yeses need to be divided into expected values, and there needs to be a proportion which is captured here. So 4 is divided into this proportion to get yeses here, and into 5 by 9 proportion to get the false values here. And the same is done for the no's. So we have 4 expected values with us and 4 observed values. Now, next step is calculation of chi-square using this formula. And by implementing this formula, we subtracted observed minus expected whole square divided by expected, and we found these values. And now we take the sum of all these 4 values to get a total chi-square of 2.72. So we found that chi-square was 2.72 for attribute 1, and the same process was repeated for attribute 2, and we got a chi-square of 0.088. So from these we see that attribute 1 is giving us a better value of chi-square. It is capturing the relationship better. So we select again attribute 1 is a better split when we use chi-square as a metric. So I hope all 4 metrics are now clear, which are used to decide, which are used to take the decision to split the tree further, and which will lead us to purer nodes in the fastest and the most efficient way. So thank you for joining, and keep tuning in. Keep checking out this series of decision trees. We will cover from the basics to the advanced level, and how the decision trees are implemented in actual as a use case in Python. So all this will be covered, and this series aims to simplify and cover the concept, the algorithm of decision trees in the best possible manner. Thank you for joining. Thank you.